Welcome back. In section 4.2, we'll be looking at orthogonal bases and projection. Our goal is to define for any finite dimensional subspace W of an inner product space V, we want to construct a projection map, projection of W from V to W onto W. All right, so we're after projections like we had projections in Rn. To do that, we need first to construct special bases. Those are going to be called orthogonal bases. To get these projections, we first need to learn about special bases called orthogonal. Let V be an inner product space. Let S inside V be any subset. S is called orthogonal if for any V in W, well, they're orthogonal, so V is perpendicular to W. We'll write it as V W is 0, but really all right, so let's consider V with the usual dot product. I'm going to consider this set S. I want to show that S is orthogonal. So I need to check that any pairs of vectors in that set are orthogonal. So I'm going to need to compute V1, V2. The dot product, I need to compute V1, V3. And I need to compute V2, V3. I need to check that any pair is orthogonal. So V1, V2, that will be 1 times 1 plus 1 times minus 1 plus 0 times 0. That is 0. V1, V3, that's 1, 0, 1, 0, 0, 3. And similarly for V2, V3, I get 0. So S is orthogonal. All right, Theorem 4.2.1, let S be an orthogonal set of non-zero vector, then S is automatically linearly independent. This is an interesting one. I like it because we're talking about orthogonal that depends strongly on the inner product you chose, but linearly independent, that just lives on the level of vector spaces. So let's prove this. So let's assume that I have a linear combination like this, that it gives you 0. All right, so I'm going to look at what happens when I take the product of VI with one of these things. So VI times A1 V1 plus AN VN. That's going to be A1 V1 V1 plus the only one that's going to be interesting is this one here. All the other ones will give me 0 as we assume we have an orthogonal set. So all of these are 0 except for this one. And so what I get, oops, sorry, I get AI, VI, VI. And on the other side, I know that this is 0, and so I get VI on 0, I get 0. And so we know that AI, VI, VI, that's equal to 0. But I have non-zero vectors, and so this part isn't allowed to be 0. We get that AI equals 0. And then that's true for all of them. You just have to dot it with a different vectors, and so S is linearly independent.